Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay. Good afternoon, everyone. Can the people at the back hear me? Okay. Yep. Right. Just a couple of announcements before we begin. The assignment results will be made available later today. So probably in the evening you can check your exam score or assignment score. Just a couple of points. When you go through your assignment, you'll see the grades and the comments from the markers. Okay. If you have any issues, please refer to the solutions guide that will also be made available on Wattle later today. Okay. Now, don't treat the solution guide as the only possible solution for the assignment. Okay. It's a guide. It's sort of giving you a template as to what is expected or what was expected in the assignment. Okay, given that this is a modeling sort of technique, a modeling assignment, it obviously there are lots of different options and lots of different ways in which those same questions can be answered. Okay. Secondly, for some of you, very few of you, your final score will not match what is there in the marked assignment, okay, the document that you uploaded, and that's because you've handed in your assignment late, okay. So as you know, if you've handed in your assignment late, and if you've not gotten the approval for handing in your assignments late, there's a 5% penalty for each day, okay. So for that reason, you will see a slight difference in the grade that you've got. Okay, this only applies to maybe 10 or 15 students in the entire class. So for most of you, this doesn't really apply, right? What you see on the graded assignment is what your final score is going to be on the grade book on Wattle. Okay. Again, keep in mind, this assignment's worth, I think, 15% of your overall score, okay? Second assignment will be made available to you on Wattle sometime next week, early next week, okay? And for that, you'll have another couple of weeks to go through the assignment and submit your work solution. Okay, starting from tomorrow's tutorial, and following into next week's tutorial, your tutors will spend some time in going through the assessment, okay, meaning going through the solutions, answering questions that you may have, right? So if you have a tutorial today, don't ask your tutors about it, right? So until you've seen your actual assignment, don't ask your tutors about it, but once you've received it, so starting tomorrow, you can talk to your tutors about any issues that you have, okay? Again, keep that in mind that the tutors are not responsible for changing your mark for the assignment. So if you have any concerns regarding change in mark, right, so you feel that you've not got the right grade or any issues related to actual marking, okay, you need to speak to me. Okay, so send me an email or come to my consultation hours and we can sort it out, right? You can talk to your tutors about, you know, what was wrong and what, you know, where did you go wrong and so on and so forth. Okay, they can help you with that, but they cannot change your mark. Okay, whether it's justified or not, they cannot change your mark. Okay, so the only person who can is me, and so you must come and talk with me. Okay. Any questions? No? Okay. Let's then get back to our regression exercise, right? So yesterday we looked at multiple linear regression within qualitative or a categorical variable fitted into our model, right? So we're going to continue from that point on, right? So just a quick sort of a recap. What we started with was a situation where we are trying to assess the price of a house, okay? Now obviously we are modeling the log of price rather than the actual price. And one of our predictors was the square foot living area, okay, which is denoted in this variable, SQFT underscore living. Okay, again, for that variable also we took a log transformation, okay, because that made our relationship linear, as we can see here. And then we added one categorical variable, which was all about whether the property has a waterfront, right? So it's on a lakefront or any sort of a water body is in front of that property. Okay. The last model that we considered was fitting a linear model with the different slopes and different intercepts. Okay. Particularly different slopes and different intercept for that categorical variable called waterfront, right? We did that using an indicator variable, a dummy variable, right? And just a quick recap, D1 was going to be equal to 1 if the property has a waterfront, and D1 is equal to 0 if no waterfront. Okay, right. And so essentially the different slope, different intercepts comes from the fact that our original model, which looks like this one here, okay, the different slope is introduced to this model through the presence of this interaction term. Okay, if you don't have the interaction term, then you essentially have a different intercept model but not different slopes. Okay, but when you have an interaction term, you get the idea of a different slope is also introduced, right? Which basically means that the rate at which the log price changes, which is our variable y, in relation to the log or square foot living area, is dependent on whether the property is on waterfront or not, right? So the rate of change for the price in relation to square foot living area, we saw from our data and from our results of the model, is higher whenever the property is on a waterfront, right? We saw that because beta 3, the coefficient for the interaction term, was positive, okay? It also has a different intercept because this beta 1 term for that D1 variable was also non-zero and positive, right? So properties on a waterfront have a higher intercept to begin with, okay, right? And also the fact that it changes with respect to square foot living area at a different rate, okay? That's the summary of the model that we got. We assessed each of the significance of each of the different estimates, so beta 1, beta 2, and beta 3, either using their corresponding t-statistics, right? That was one way of doing that. And the other one was looking at the overall F-test, right? When dealing with the F-test, we know that in order to use the F-test appropriately, in order to use the ANOVA output appropriately, we must be careful about the way or the order in which the variables are plugged in, right? The terms or the coefficients that you want to test must be added on last, okay? Again, I won't spend too much time on it. We spent a lot of time last week on it. This is all to do with how ANOVA decomposes the variance, right? So the decomposition of variance is done in a sequential form, right? And so in doing that decomposition in a sequential form, we need to ensure that the parameter that we're trying to test is the last one fitted, right? Because that will then measure what proportion of variance is explained by that parameter once everything else has been fitted. Okay? Does everybody get that? Right? And so that's why we always fit it that way. In terms of the applications, we have a workaround of that ordering of variables or ordering of parameters, okay? In that we can always deal with fitting two models and comparing those two models rather than just looking at a fit of a single model in the right order. Okay, the way you do that with a double model scenario is that you fit a smaller model and the larger model, which includes all the parameters. Okay, the larger model, as you can see here, includes all the 3 parameters that we're interested in, which is the waterfront variable, the living area, and the interaction between waterfront and living area. Okay, the smaller model is just the log of square foot living area. Okay, this comparison between the small and the large model allows us to test for the parameters of D1 and the interaction with D1. Okay, and you'll notice over here in the modeling, we haven't really bothered about the ordering of the variables, right? We haven't intentionally kept D1 and the interaction with D1 as the last 2 variables. Okay, this way of testing for that parameter significance is just much more practically convenient, right? And then you just use the ANOVA of comparing the smaller to the larger model. Okay, right? Important point to note with this particular method is that the smaller model must be nested inside the larger model. Okay, which means that the smaller model must have no other parameters or variables that is not already present in the larger model. Okay, you can omit variables from the larger model, but you cannot add any more parameters, any new parameters. Okay, does everybody get that? Right? If you do that, it will not work. Okay, it will not give you the correct result. Okay, so that's the way of performing the same test. Okay, when you really are. You don't want to bother about the ordering, okay? Again, the other place where this kind of testing is much more beneficial is when you're trying to test more than one parameters, as we are doing in this case, right? So in this particular case, our null hypothesis is that beta 2 equals 0 and beta 3 equals 0 versus the alternative that one of them is non-zero. Okay, right? Beta 2 over here is the one for D1, beta 3 is the one for the interaction. Okay, so when you're trying to test more than one parameters, this small versus large, this nested model approach is always much more easier. Right? Okay, again, the reason for that is if I go back to that ordered model, okay, so this ANOVA where we fitted D1 and the interaction with D1 last, as I said, we can still use this to perform that same test, that same hypothesis test, but this will require us to combine the sum of squares for both D1 and its interaction together. Okay, so the F statistic over here would be the sum of squares of these two taken together, divided by its degrees of freedom, which in this case would be 2, divided by the mean squared error. Okay, which would be 3172.6 over 21609. Okay, so it requires some extra computation that you would need to do. Okay, again, in this case, not that difficult, but if we have at our disposal some method which can do that calculation for us, why not use that? Okay, right? Is everybody clear on that? Yep. Again, going back to the summary table, notice that these t statistics, this t-test, the t-value and the corresponding p-value, performs a similar kind of a hypothesis test, okay? In this particular instance, it is performing a test of just one parameter at a time, okay? And the condition is that all other parameters, therefore all other variables, are fixed in the model. We don't tamper with those, okay? Right? So for example, for this particular test statistic and its corresponding p-value, okay, the hypothesis is that beta 2, so that's beta 1, that's beta 2, that's beta 3. We are testing specifically that beta 2 is 0 versus the alternative that beta 2 is non-zero. Okay, the test statistic is calculated slightly differently. Remember, it's based on the t distribution. So the test statistic is the value of the estimate, so that's B2, over its standard error. Okay, so it's essentially this number 0.82169 divided by the standard error 0.00619, which will give you 132.738. Right, and you compare it to the appropriate t distribution to get the p-value. Okay, right? But again, this test is performed in sort of isolation. It just assumes that all other variables must be in the model. Okay, they cannot be taken out. Right, and so you can interpret each of the three, as well as the one for the intercept, in the same fashion. Okay, right. Okay, now just one final note regarding that small versus large model comparison. You'll notice that I've done the ANOVA tables for both versions where, for example, in the larger model, I've not really concerned myself with the ordering of the variables, okay? And the other large model where I have ordered the variables in the way that I would like to test them. Okay, but you'll notice no matter which way I set it up, the F statistic, the test statistic, is identical, right? Which supports the argument that, you know, when you're comparing a small versus large model in a nested form, the ordering is irrelevant. Okay, so here the F statistic is 312.12, and same is the case in the other one. Okay, so as we can see, the ordering doesn't really matter. Okay, we're testing small versus large, and therefore you're essentially testing all those extra variables that you have in the larger model. Okay. Now, before we proceed on further, there's one sort of practical purpose that we want to talk about. Okay, now. Up until now, whenever we wanted to include that waterfront variable, we created this D1 variable, right? Which was an indicator of whether the house had a waterfront or not, right? So we coded D1 to be equal to 1 if there is waterfront, okay? And D1 is equal to 0 if no waterfront. Okay, right? Now, in cases where you have a categorical variable which has different categories, multiple categories, in this case we have 2 categories, which is fine, but even if you have more than 2 categories, and if the variable is coded that way, right, with numbers or with letters and so on, we don't really have to create a dummy variable or an indicator variable like this. Okay, we can just use the variable itself, in this case the waterfront variable, by its name, right? We can use that in our modeling. Okay, so we don't have to create a separate D1 variable or a dummy variable for each categorical variable that we want to model. Okay, the only thing that you have to be careful about is not all the times variables are coded correctly. Okay, so in this case, for this data set, so the housing data set, waterfront has values 1 and 0 in its rows, right, for each of its observation, right? When R reads that particular variable information, given that the values are 1s and 0, it automatically treats it as a numerical variable, right? Meaning it treats the value 1 as a number 1, and it treats the value 0 as a number 0. Okay, right? Whereas the way we interpret waterfront is that if it's 1, it's a code for yes, there is a waterfront. And if it's 0, it's a code for no, there is no waterfront, right? Okay, so we're just using 0 and 1s not as numbers, but as codes, okay? Right? So in order to tell R that information, give R that information so that it can correctly use that variable, okay, we use this function called factor. Okay, so factor is a function in R which treats the argument that is given to it, okay, the option that is given to it, as a factor variable, as a categorical variable. Okay? Does everybody get that? Right? And so it will treat the numbers 0 and 1 not as numbers but as codes to represent something. Okay? Right? Again, R doesn't know what it is. R doesn't know that 0 means no waterfront and 1 means yes waterfront. Okay, that's something that you as a user will interpret it as, but at least now it's coded correctly. Right? It's treating the numbers not as numbers but as codes. Okay? Right? And so when we apply the levels function to the factor of waterfront, you will get the correct result of providing you 2 levels. Right? The 2 levels of that factor variables are 0 and 1. Okay? As an exercise, I'm not done it here. Try to run this command. So levels of waterfront. Okay? So without the factor, just run the command levels of waterfront. Okay? You will see that the result for that is NA. Right? The reason for that is waterfront itself is not a factor variable. Okay? And so there are no levels in it. It just has numbers 0 and 1, which is treated as numbers 0 and 1. Okay? Right? Now, in the actual modeling, as you see at the bottom, now we are not using D1. We are using this variable called factor of waterfront. Okay? In the interaction term, again, instead of D1, we say factor of waterfront. Right? Okay? And this is a better way of modeling. Okay? Firstly, we'll see when we look at the outputs. So when we see the summary output, you'll notice now waterfront, which earlier used to be labeled as D1 in all our outputs, is now labeled correctly using the variable name. Okay, so any user who sees the results can understand what that represents, right? In the previous results, it was always D1, okay? And unless you know what D1 is, you are really at a loss to understand what that result is all about. Okay, right? Again, the other thing it gives you here, notice that it has a value added on at the end, right? Okay, that is the value that is coded as. Remember, when you fit a model with D1, okay, the way we interpret this information is whenever D1 is 0, right, that particular outcome does not lead to a value for beta 1. Right? But whenever D1 is 1, it adds to the value of beta 1 to the final response value. Okay? Right? Which essentially means that for those points where there is a waterfront property, right, we get that model as our equation, or we get that as equation as our model. Okay? And whenever there is no waterfront, we get that model. Okay? The 2 separate lines. Right? It's the same thing which is happening when we use factor of waterfront. Okay? And what it's saying is in the factor of waterfront, okay, it is treating the 0 value, okay, the 0 level, sorry. It is treating the 0 level as your reference level. Right? It's the level with which, in reference to which, that particular variable is coded, that particular variable is interpreted, right? So this this particular estimate that we get, okay, is for when waterfront is equal to 1. Right? Okay? Right, again, using different labels, but it'd be essentially getting the same model as before, right? So if you were to look back, go back to our summary for the original model, you'll see that the estimate is exactly the same, right? The estimate when we were using D1 was negative 1.415, right? Back to our new method. The estimate is again exactly the same, right? Does everybody get that? Okay. Now the way R treats referencing, okay, is that it picks the first level as the reference level, right? So given that the two levels are 0 and 1, it will pick the 0 level as the reference level. Okay, right? If instead of using numbers as codes, you're using alphabets, so letters from the alphabet, like A, B, C, or names and so on, again, it will do it in the same way. Okay, it sorts all the levels alphabetically, it picks the smallest, the one that begins with the earliest letter, as the reference level. Okay? Does everybody get that? Right? If you want to change the level of that factor variable, right? So for instance, you're not really interested, you're interested in non-waterfront properties as compared to waterfront properties, then you ideally want 1 as your reference level, right? Because you want to compare non-waterfront properties to waterfront properties. You want to see what having a no waterfront does to the price model. Okay? And then you really want 1 as your reference level. Okay? Then the command that you use is relevel. Okay? I'll show you in just a few minutes how that actual command is used. Okay? What is its syntax? Okay? But the relevel, essentially, as the name suggests, it relevels the level of a factor variable. Okay? In the particular level that you want. Okay, all that relevel really does, it allows you to choose which level you want as the reference level. Okay, again, I'll come back to the syntax for that later. Okay, so right now, all we've sort of done is gotten away with having to use a new dummy variable every time we have a categorical variable, right? R can model the variable itself if coded incorrectly, right? So all you have to do is use the command factor of the variable to correctly use it, right? Okay. Now, if you really want to save some time, what you can in fact do is save this factor of waterfront as a new variable, right? Okay. So in fact, what you can do is say waterfront is as dot factor of waterfront. Okay, or factor of waterfront. Okay, you can use as dot factor or just factor itself, right? Both of them will work. Okay, and I'm using the same name again so that it gets coded back into that same variable. Okay, right? Again, if you want it in the same data frame, our h.data frame, okay, make sure you correctly identify it. Okay. Does everybody get that? Right. So what we've done is recoded waterfront as a factor variable and saved it back in the original data frame. Okay. Right? Now that waterfront variable is no longer a numeric variable. It is identified correctly as a factor variable. Okay? Right? In that case, we don't, every time when we fit the model, we don't have to write factor of waterfront. We can just simply write waterfront. Okay? Because we've already coded waterfront as a factor variable. Okay, that's just our tip to make work easier. Okay, but if you don't really want to, rejig your data frame every single time, which is generally a good idea when you're sort of beginning out, right? When you're still uncomfortable working with R and so on, this is a much easier way, right? This does not destroy the structure of the data set that you have. Right? You just, every time that you want to treat the variable as a factor, you just provide the command. Okay? Right? Any questions? No? Okay. So, as I said, this now allows us to not having to rewrite or recode a new variable, D1, right? We can just use factor. Okay? The good thing is when you treat a variable as factor, okay, the ANOVA for that table, for that model, treats each levels of that factor into a single variable as it should. Okay. Now, when your factor itself has just two levels, okay, that information is not really clear, right? So, as we can see in the ANOVA, okay. Given that D1 or waterfront is a single, is a binary variable, meaning just has two levels, okay, you obviously only have one line for that variable, right? But let's start by looking at a situation where we have a factor variable with more than one levels, okay? So another variable in that same data set is called condition, okay? The condition has 5 levels. Okay, they are coded as numbers 1 through 5, as you can see from that command levels of factor of condition. Okay, condition has to do something with the condition of the property, right? So it's a qualitative measure of the condition of the house. Okay, I'm presuming 1 refers to the condition being the worst, and 5 being the best. Right? Okay. So the higher the number, the better the condition is. Okay. Right, of that house. So if we want to now include this variable in our multiple regression model, okay, we can do so by using the command factor of condition. Okay. Now, before we look at the multiple linear model with factor of condition and other variables, let's just look at that condition variable itself. Right? So as you can see, if you look at the box plot of the price, the log price, with the different levels of condition, you notice that as the condition value increases from 1 through to 5, the log prices also increase on average. Right? Which suggests that obviously the house with the worst condition will have a lower price. Okay? And as the condition increases, the price sort of increases along with it. Right? Okay. It's not a perfect relationship, which is fine because again there are other factors which as we already know from the models that we fit, which determine price. Right? Condition is not the only variable. Okay. So there could be other reasons why the structure sort of plateaus out as the condition improves, right? But again, we'll talk more about that just in a little bit of time, but we at least know the general pattern, right? Condition improves, the price typically increases. Right, so now let's fit a model which has just condition as our single predictor, okay? Right, now notice from yesterday, when you only are using a single categorical variable as your predictor, essentially what you're doing is you're trying to compare the different group means, right? So in a way, what you're trying to do in that model is to compare the average log price between the 5 different conditions, right? Is it statistically different between the 5 groups? Okay, that's essentially the test that we want to do. Right? Now, we saw it yesterday when we were using the waterfront variable that you can do that without actually fitting the regression model. Okay? You can just perform a simple t-test of comparison of means. Okay? But regression allows us to do that as well as talk it gives us a lot more information, right? And that's why we do regression rather than just doing a simple t-test, okay? So as we can see here, notice that if we were using the dummy variable approach, okay, and not this factor of condition approach, then in order to treat the 5 separate conditions of that condition variable, the 5 different levels, we would have to create 4 dummy variables, right? 1 to represent each of the different conditions other than your reference level, the reference condition. Okay, right? Now this allows us, this way of writing the model allows us to do exactly that without having to create those 4 dummy variables. Okay, right? So R can understand how to correctly code or model with a factor variable. Okay, it does that dummy variable creation on its own. You don't have to explicitly do that. Okay, and as you can see in the coefficients, it does provide you with 4 separate coefficients for the 4 separate condition values apart from your reference condition. Right? Now, if you go back to our model itself, right, this is in fact the model that we are trying to fit. So we're fitting log price equals beta 0 plus beta 1, okay, D1, and D1 represents that condition equals 2 plus beta 2 D2, that's condition equals 3, plus beta 3 condition equals 4, plus beta 4 condition equals 5. Right, so that's the model that we are fitting. Okay, 1 parameter for each different condition value other than your reference condition value. Okay, right? And so we get these 4 estimates for those 4 betas. Right? So beta 1's estimate is 0.046, right? So that's that. Okay, beta 2's estimate is 0.56521, so on and so forth. Right? Okay, now the first question that we must ask ourselves is, what are these estimates actually estimating? And what are they actually giving us values for? Okay, what does this beta value for beta 1 of 0.04693 actually means? Okay, what is it trying to measure, right? So in order to sort of understand that, let's look at that in a greater detail, right? So again, the model that we're trying to fit is log price is beta 0 plus beta 1 condition equals 2 plus beta 2 condition equals 3 plus beta 3 condition equals 4 plus beta 5 condition equals 5. Sorry, beta 4. Okay, what this means is, if you have a property which property's condition value is, say for example 3, so property where condition equals 3, okay, then your model looks something like that, right? So I'll just use y, so y hat equals beta 0 plus beta 2, right? The rest of these would all take on value 0, okay, and so they will all be suppressed. Okay, if condition equals, for example, 1, which is a reference condition, okay, then your model essentially is y hat equals beta 0. Right? Okay. Now, what are these y hats? Okay, if we go back to very beginning, week 1, week 2, okay, it's nothing but the expected value of I given x. right? Which essentially tells us, particularly for this when condition is equal to 1, is it's the expected value of price, or log price in this case, when condition is equal to 1. Okay? Meaning it's just the group mean when condition equals 1. Right? So it's an estimate for that. So it's mu hat. Okay? All right. Similarly, this would be expected value y given condition equals 3. Okay, right. In fact, this, and given that we know that beta 0 is mu hat, or beta 0 hat is mu 1 hat, okay, we know from this that beta 2 must be mu 3 hat minus mu 1 hat. Right? Okay. Is everybody clear with that? Just another example. So say when condition is equal to 2, okay, our model is y hat equals beta 0 hat plus beta 1 hat. Okay. This by definition must equal expected value of y given x. In the x is your condition variable, which must equal mu 2 hat. Okay, and so beta 1 hat must equal mu 2 hat minus beta 0 hat. Okay, but we know that beta 0 hat is mu 1 hat. Okay, it's the group mean of log price when condition equals 1. Similarly, this is group mean of log price when condition of the house equals 2. Okay, so from this we can see that each of our estimates for these parameters, betas, except for our intercept one, so beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat, okay, in this model, so each one of their estimates are nothing but the difference between the price, the mean price, when condition equals that condition, right? So beta 4 hat for that instance would be condition mean price of a house where the condition of the house is 5 minus the mean house price, log price of a house where condition of the house equals the reference condition, which is condition equals 1. Okay? All right, so these estimates of betas for our factor variable represents the difference in mean. Okay? Right? Difference in mean in comparison to our reference category. Okay, so each category being compared to the reference category, right? Okay, and that's why we said yesterday when we just had 2 levels, 2 categories, that we can use the result of a regression to test whether the means are different, right? Because again, in that instance, we got the same result. Over there, it was a lot more obvious to follow because we just had 2 categories, okay? Now that when we have multiple categories, it's a little more difficult to follow, right? Okay, but it still represents the same thing, right? Each of these estimates just represent the difference in mean with reference to the reference category. Okay, right? So now these 4 estimates for beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat, have allowed us to compare the means between the group 1 mean, so when house price, when condition is 1, versus house price when condition is one of the other 4 categories. Okay, but what if I want to compare the house price, so log price, when condition equals 3 versus log of price when condition equals 4. Right, so if I want to compare mu 3 versus mu 4. Okay, how can I do that? Does this model allow me to do that? So the model that we've got above here, does it allow us to do that? No, because all the 4 means that it does compare are in reference to our reference category, which is category 1. Right? Okay. Does everybody get that? Right? So in fact, if we want to compare that, so if we want to compare mu3 versus mu4, we'll need to come up with another way. Okay? Can anybody wants to guess as to what we need to do? Yep. That's correct, but what if I want to use regression? What do I need to do in regression setting to do that?
You make 2 different models. One model nested within another, one that adds people.
No. It's a much more simple. You can't really do that 2-model thing because we just have one predictor here, condition, right? Remember, you just have one predictor condition. Okay, it's a very simple, elegant solution. You change the reference category, right? You just re-level the factor condition where you set the new reference category to either condition 3 or condition 4, right? Then if you look at the model results from that, okay, then each of these lines here will be a test of comparing the group mean of that category versus your new reference category, say condition 3, right? Okay, we'll come back to that in just a quick second. Okay, but right now let's do these comparisons, right? So let's compare these group means, these 4 that we can do. Now notice the p-value for condition 2. Okay, the p-value is 0.65, much greater than 0.05. Okay, which we would have ideally chosen, our alpha level of 0.05, which suggests that that particular null hypothesis, we do not have enough evidence to reject that null hypothesis, right? So we must accept it at this stage, right? Which means that the group mean between group 2 and group 1, meaning condition 1 and condition 2, is the same. We don't have evidence to say that it is different, statistically different from each other, right? Okay, for the other 3, the p-values are much smaller than 0.05, right? So we can over there state that in fact the group mean of the other 3 conditions are statistically different from group 1 mean. Okay, right? But again, how many tests did we perform here? Tests of comparison? 4, right? And we are performing all those 4 tests with the same model, with the same single variable, right? Okay, so remember again from last week, if you're performing multiple comparisons with the same predictor, right, you would be wrong to assume 5% level of significance for each one of them, right? If you do that, then the overall test for all the 4 factors, okay, would not have the level of confidence set at, or type 1 error at 5%. It would be much higher than 5%, right? So if you want that all 4 taken together is set at 5%, then we must perform each individual test at a much stricter level of confidence, right? So applying the Bonferroni adjustment in this case, right, rather than performing the test at 5%, we must perform each test at 1.25%. Right? Unless you do that, you're not ensuring that your overall test confidence level is set at 5%. Okay? Right? So in this case, now there's no way that we can, in fact, produce a summary result where we can change that confidence level. In fact, we don't really need to, right? It just gives you the p-value, right? So in this case now, instead of comparing the p-value to 0.05, all we need to do is compare the p-value to 0.0125, right? That's 5% divided by 4. Okay? Right? And if you do that, then we can then perform that same test, right? Alternatively, what you can do is calculate the confidence interval for each of those 4 coefficients. Okay, beta 1, beta 2, beta 3, beta 4. Calculate the confidence interval. Okay, in this case, calculate the confidence interval where the level of confidence is based on 1.25% and not 5%. Okay, right, and then see whether in each of these confidence interval the value of 0 is included or not. Okay, if the value of 0 is not included, that means that the evidence is strong to reject your null hypothesis. Okay, if the value of 0 is included in that interval, that means your evidence is not there to reject your null. Right? So in this case, only the first interval includes the value of 0. Okay, and so in this case, you must accept the null. Okay, in all the other 3, you can reject your null hypothesis. Okay, the null being each one has a separate null hypothesis, right? So the null for the first one is that mu2 is equal to mu1. Right? The null for the second one is that mu3 is equal to mu1, and the next one is mu4 equals mu1, and the last one is mu5 equals mu1. Notice how the comparison is always against mu1, not any of the others. Okay? Right. Again, a quick R tip. You notice that when we're calculating the confidence interval in the square bracket, we are trying to exclude the confidence interval for beta 0. Right? We don't really need that to perform any of our tests. Okay? Right? So that you can do by essentially specifying that I don't want the first row printed. Right? So that's why you have that -1. Okay. Another way you can write this out is rather than deleting the rows you don't want, you specify the rows that you do want, right? So we actually want the second, third, fourth, and fifth row. So you can say, give me 2 rows 2 through 5, all the columns. Again, that's why the column space is empty. Okay. Right, and that will produce the same result. Okay, does everybody get that?
Why is it 0.625?
Sorry, it should be 0.0625. Oh no, sorry, no, it's correct. Oh, it's correct. Because our confidence interval is 0.0125, right, so we are taking that amount from either side. Okay, and so you get that points. So we have 0.0125 in both the tails, right? Divide by 2, you get that much in each of the 2 tails, symmetrically. Okay. Right. No, as I was just saying, you can't, because over here, what would you compare it against? Okay, you want to test whether all of the beta 1s through the beta 5 are equal to 0. Okay, for that, yes, so you can perform. So, for example, so the question was, for those who couldn't hear, is what if you want to perform a test that each of your betas, from beta 1 through to beta 4, they're all equal to 0, right? Versus some non-zero. Okay, in that case, you can use the ANOVA table, right? But that you can more directly just do it based on the F statistic given there at the bottom, right? You don't even have to compare the small versus the large model, because that is itself done always in a typical model, right? So the F statistic at the bottom always tests for an empty model versus a full model, and that's what you're doing here. For changing the reference level, I'll come back to that in just a sec. Okay. For that, as I said before, you can't perform that test by just changing or remodeling or comparing it with a smaller or a different model, right? You have to change the reference level, okay? And so you will have to use re-level, okay? But how, in fact, we do that, I'll come to that in just a few minutes. Okay, yep. Any other questions? Oh, okay. So that allows us, as I said, to compare all these different means, okay? Now, this is the strength of a regression model as to just doing simple T statistics in comparing the means, right? I just sort of showed you that those estimates for the parameters, the betas, they essentially represent the difference in the means, the group means, okay? And so testing the significance of a parameter is equivalent to testing whether the group means are same or different, right? Okay? And if you look at the ANOVA table for such a model, okay, and that sort of answers the question that we had here, is if you wanted to test the overall model, meaning all betas equal to 0 versus some non-zero, okay, you can just look at the ANOVA results, okay? And the strength of using that factor of condition as your variable rather than using 4 different dummy variables, okay? The strength of using this is that the condition variable is suppressed into a single line in the ANOVA table. You don't have one separate line for each of the different levels, okay? Right? And therefore you can see the degrees of freedom for that variable condition is 4. Because why does it have 4 degrees of freedom? Because essentially it has 4 independent levels, right? One is your reference level, there are 4 other levels other than that, right? And it can perform that test of overall significance more directly, right? The F statistic in this case is about 76 with the p-value much less than 0.05. Therefore, it suggests that we can reject our null of that all betas are equal to, all betas are equal to 0 versus the alternative that some of the beta i's are non-zero, right? Okay, and always keep in mind the alternative is that the sum of the beta i's are non-zero, not that all beta i's are non-zero, okay, right? Which, as we can see in our previous example, is that our beta for factor 2 or condition 2 was in fact 0 based on our test, right? So that beta 1 was in fact 0, all the other betas are non-zero, okay? And it still agrees with our results here, okay? We don't need all, for the alternative, we don't need all beta i's to be non-zero, only some of them, or at least one of them, okay? Does everybody get that, right? Now, let's add a more complication. Right, so let's add back square foot of living area, okay? Right, so the practical question that we want to ask is then, so if you go back to that box plot, right, the box plot sort of suggested that the group means of the log price is different between different conditions of house, right? If the condition changes, the price is expected to change. Right? And we tested for that, we saw evidence of that, and all that's good, right? But just like when we did it for waterfront, we can further say that the difference is not because of condition itself, but because of, let's say, living area, right? The larger houses, again, would have higher prices, okay? And it could be conceived that the newer houses, or the condition, where the condition is higher, are potentially houses which are also bigger, and that's why we are seeing larger prices, okay? And so again, the question is whether condition is still important once you factor in the living area, okay? And for that reason, we add log of square foot living area into our model, right? So now we have a model which has log of square foot living area and has factor of condition. Okay, looking at the summary results of that, we notice again, just like before, okay, log of square foot living area is significant as long as you have everything else in the model. Okay, but what we notice more importantly is that condition is now not as significant, right? Particularly if the condition is anything of 2, 3, and 4, okay, each of those produce a non-significant parameter. Okay, right? Only the fifth one. So if the condition is 5, meaning the best of the lot, then you have that particular condition as a significant predictor, right? So beta 5 in this case is significant, right? Okay, again, if we want to look at the model itself, right? So the model that we're trying to fit is y hat equals beta 0 plus beta 1 x1, which is a log living area, plus beta 2 condition equals 2, plus beta 3 condition equals 3, plus beta 4 condition equals 4, plus beta 5 condition equals 5. Okay, so that's our model. In fact, given that's a fitted model, should use that. Okay, so that's the model that we are getting, right? Okay, and what we're basically seeing here is evidence that only beta 5 is significant. The others are not significantly different from 0. Okay, but the first question sort of we should ask is, those betas, particularly for the factor variable, do they still represent the same thing? Meaning, those estimates that we've got, do they still represent, okay, so for beta 2 through to beta 5, do they still represent, okay, the difference between that group minus the reference group? Okay, when we just had condition, we showed that the betas essentially are difference in the means, right? The mean of that group minus the mean of the referenced condition group, right? Okay, but now that we have a new variable, an extra variable, do those beta still represent the same thing? Okay, the short answer is yes, they still do. Okay, in fact, as long as you don't have the interaction term, okay, those betas will always represent the difference in the group means. Okay, if you have interaction, it complicates the scenario much more. Okay, we come to that a little later. So these betas still represent the same thing, okay? Again, it's easy enough to see how, right? So let's say you're comparing two houses, okay, where one house has condition 3, okay, and the other house has condition 1. Everything else is the same, right? So they have the same square foot living area, okay? The only difference is that one has got a condition value of 3, the other has got a condition value of 1. Right? If that's the case, then the y hats for those two houses, so y hat when condition is equal to 3 would equal beta 0 hat plus beta 1 hat times whatever its living area is. Let's say it is some value x plus beta 3 hat. Okay? And for y hat when condition is equal to 1, it would be beta 0 hat plus beta 1 hat, the same living area x, right? Okay, in that matter, if we take the difference of these two equations, then we would get y hat when condition is 3 minus y hat when condition is 1 equals beta 3 hat. Okay, why do we get beta 3 hat on the right hand side? Everything else cancels out, right? This minus the first equation minus the second equation, the beta 0 hats will cancel out, beta 1 hat x also cancel out, all you're left with is beta 3 hat, right? So beta 3 hat represents y3 hat minus y1 hat. Okay, but what are y3 hat and y1 hat? It's the expected value of y given x, right? So it's essentially the group mean of condition 3 minus the group mean of condition 1. Okay? Right? So we still get the same result as before. Right? So the betas of your categorical or the factor variable always represents the difference in group means. In particular, it's the difference in group means from that condition to the reference condition. Okay, from that level to the reference level, whatever reference level you choose. Okay, right? So again, testing for the betas individually, so beta 2, beta 3, beta 4, beta 5, is the same as testing for whether the difference in group mean is equal to 0 or not. Or, equivalently, it is testing whether the group means are equal or not. Okay, right? If you're looking at the ANOVA, just as before, the ANOVA allows us to do overall comparisons, right? So if you want to compare the whole of the factor condition as a whole, not individual levels, but all the levels together, okay, then you can use the ANOVA, right? Where make sure that factor of condition is fitted in last, right? So that allows us to test, in this case, whether you should incorporate condition as a predictor. Okay, in this case, you'll notice that the p-value is much less than 0.05, and so it suggests that you must, not must, but you can include condition as a predictor, right? It is statistically significant. Okay, from the above result, we have seen that in reference to level 1, it's only level 5 which is significant. The others are not statistically significant, but that is good enough. That is good enough to have condition coded in, right? Okay. Now, in fact, okay, I'll come back to the addition of interaction a little later. Okay. Let's come back to that original sort of the previous question that I had asked was, what if you wanted to compare the group 3 condition, so the level 3 condition versus level 4 for that matter, okay, or level 2 versus level 5. Okay, how do you then do that, right? So the idea was you can re-level your factor variable. Okay, right? Now the question is, how many such comparisons are possible, right? So we've seen in our first modeling, the first model that we fit, right? We've done 4 comparisons, right? It was 2 versus 1, 3 versus 1, 4 versus 1, 5 versus 1. Okay, right? Can anybody answer how many such comparisons unique comparisons are possible, right? So we have condition variable which has 5 levels. Okay, so for a variable which has 5 levels, how many unique comparisons can you do? Well, given that you can form pairs of 2 comparisons, right? Each comparison has 2 levels, right? Out of 5, if you compute unique choices of pairs, okay, then essentially there are 10 pairs that you can form, right? Again, it's a simple combination or permutation option where you essentially from 5 you try to make pairs of 2s, right? So 5 choose 2, which gives us 10 unique pairs and 10 unique comparisons, right? In this case you can easily list all of them very quickly, right? So we already have 4, which is 1 versus all the others, right? The others would then be 2 versus 3, 2 versus 4, 2 versus 5. So that's 3 more. Then we have 3 versus 4, 3 versus 5, and then finally 4 versus 5. Right? Okay, so there are 10 possible pairwise comparisons that you can perform, right? Or 10 possible mean comparisons that you can possibly perform, and that you should in fact actually perform, right? If you want to correctly answer the question whether the group means between the different groups are equal or not, you must compare all these 10 pairs of means. Okay, you can't just do 4 and say that that's enough, right? You must do all 10, right? How do we then perform that? Okay, now before we do that, I'll just show you very quickly how we can use R to do all of this rather quickly, okay, rather than doing it by hand, right? So the first thing we do is use R to evaluate these group mean differences, right? So notice how these estimates for the betas represents the difference in the group mean, right? So this estimate for factor condition 2, we know represents mu2 hat minus mu1 hat, right? Okay, so if you want to find that using the output from your model results, okay, the way we can do that, okay, is by using the predict command. Okay, so in the predict command with our chosen model, okay, we specify the condition that we want, right? So if we choose or set condition to be equal to 1, okay, choose your living area to represent the mean. Okay, and that's very important. Remember from our theory of regression modeling, okay, when every predictor is set at its mean value, the response that you get is also the mean value, right? Okay, remember, or sort of what we've actually seen this as in our modeling is that X bar, Y bar is always on our regression line, is always on our fitted line. Okay, if you choose the mean for all your predictors, then by default the response has to also be the mean. Okay, so for that matter, if you use the predict command, when you set square foot living area as the mean value, okay, and set condition to be equal to 1, then by design the predicted value must equal mu1 hat. Okay, I've coded it as mu dot hat dot 1. Okay, right, so this has to be with mu1 hat. Similarly, if I do the same predict command, but now if I set the condition to be equal to 2, okay, then I necessarily must get mu2 hat. Okay, similarly, I've done that for all the other 5 condition values, right? All the other 3. And so we get mu3 hat, mu4 hat, mu5 hat, right? Okay. Now, if you're still not convinced as to whether this method works, okay, then there's a quick test, right? We've seen before that, for example, the coefficient that goes along with condition value 2, which was, so in our model, which was beta 2, right? Its estimate is negative 0.088, right, approximately. Okay, so beta 2 hat is 0.088, right? We've just shown before that beta 2 hat is nothing but mu2 hat minus mu1 hat, right? Now, if these values are correct for the mu's, then taking the difference between mu2 hat and mu1 hat must give us the same value, right? For that matter, taking the difference between mu3 hat and mu1 hat must give us beta 3 hat, okay? Mu4 hat minus mu1 hat must give us beta 4 hat, right? So let's in fact do that, and that's beta 2 hat, right? See, we get the same value, okay? For the next one, we get beta 3 hat, right? So again, check beta 3 hat, is it 0.07335? Yes. Okay? In fact, all the others are also correct. Okay? So this way of setting up or evaluating the mu's, the group means, is correct. We do get the group means. Okay? Right? Now, why did we do that? Okay. Now, all I want to do as a